Hello and welcome to my video where I'm going to talk about work and energy in a physics sense or a scientific sense. So first of all, let's just think about force. So force is, why is it not doing that? Hold on, I want to not use the lasso tool. There you go. Okay, anyways, force is imparted onto an object. So one thing does something to another, okay? So whether that be gravity is acting upon an object, or a person is pushing against an object or pulling an object, it's a push or pull on an object, okay? And it's measured in newtons. This is the SI unit, or the scientific unit, or the standard unit. So the formula for force is F equals ma. So F is force, m is mass. So maybe I'll just write that down. Mass, and a is acceleration. So if you remember from previously, when we talked about vectors and scalars, if we're multiplying by a vector, so acceleration is a vector, that means it has a direction, which also means that force is going to be a vector. So acceleration has a direction, and force therefore also has a direction. So if you think about it, a force is a push or pull, and it matters what direction it is, because if we're adding up forces and two forces are in opposite directions, let's say one's going to the right, one is pushing to the left, they're going to push against each other and they might not move. So if I push against a desk, for example, the desk will push back against me and the desk won't move. I'll feel the force in my hand of the desk pushing back. Okay? So let's keep all that in mind, as well as, again, the units are newtons, which is an N, or represented by an N. And mass is kilograms, acceleration is meters per second squared, and so a newton is a kilogram meters per second squared. Kilogram times meters per second squared. So that is force. Okay? Work is a measurement of the force times the distance. Okay, so it's force times the distance, FD. Or you could break up force into mass times acceleration, and break it up even further. So if you wanted to get the units, you could get the units for, units for force is in joules. For work, is in joules. And so that would be the J. But the D is meters, m is kilograms, a is meters per second squared. So meters per second squared times meters, so we've got meters squared per second squared. So there's the 2 here because the d, or the distance, or the displacement, is multiplying against the acceleration. Okay? So basically, work is a force carried out over a certain distance. Okay, and it's energy transferred from one object to another. So, for example, I can do work by lifting a ball up in the air. So what's happening is I'm transferring my chemical energy into my body, from the food that I ate, and the ATP in the cells, all the way I'm changing it from chemical energy into mechanical energy, or another word for it is, in this case, potential energy, gravitational potential energy. So that would be an example of energy transfer. Or if you push something up a hill, same thing. Or if you push something sideways, but there's friction, okay? You're transferring your energy into the friction, which is the heat. Okay, first it transfers into kinetic energy, and then into friction. So work is done when there's energy transfer. It's done on or by an object, which also tells you, again, because it's being multiplied by a vector, it also matters what direction. It is also a vector. Okay, on the other hand, energy is measured in joules just the same way, but it is a measure of the total energy, the ability to do work. This is a scalar. Okay, it is the ability to do work, the potential energy. When we talk about that, it's what could the object do. So if you talk about the chemical energy in my body, that would be what could my body potentially do. And you could measure that in joules for sure, but it is a different thing than the work, which is very specifically when we're doing the energy or using the energy to do a task. So force and work are both scalars. I just said that, since they come from acceleration, which is a vector. What if we have balanced opposing forces? So you can think about it, like I said at the beginning, if you have arrows, vectors are arrows, you can kind of represent them by arrows. And if you had two opposite arrows and they were balanced, what happens is that they cancel out exactly. If they're completely balanced, nothing happens. Okay? So in this case, actually, nothing happens. Zero acceleration. Okay, you can imagine that if there's no force, then there's no acceleration. Okay, if we have unbalanced opposing forces, so let's say one is pushing this way with that much, the length of the arrow kind of represents how much force, and maybe this one has half as much force. Well, what's going to happen is when we add those two together, the resulting vector arrow is the leftover length, or the leftover, it's basically if you had both as numbers, so it was like 4 and 2, you'd be 4 minus 2 to get your next force. And so here is when we'd have some sort of acceleration. Some acceleration. Okay, so let's just think about these cases down here. These are cases of zero work. Okay, so what could possibly happen to give us zero work? Well, if we think back to our formula for work here, work is force times distance. So it's zero work if the force is zero, right? That makes sense because of our formula. So if F equals 0, it's also zero work if distance is 0. So that makes sense because if either one of those values, here or here, is 0, the whole thing goes to 0. Okay? And because work is a vector, it does need to have both the movement and the force in the same direction. This matters a lot. Okay? Because it's a vector, they do have to go in the same direction. Okay, so let's just take a look at these couple examples. Just before we do, I want to say, just as a reminder, nothing is 100% efficient, and that's nothing at all, ever. Cars are really inefficient. Refrigerators, Teslas are really inefficient. Hybrids are inefficient. Trucks, vans, planes, you name it, they're all inefficient. There are some things that are pretty good, but the closest you'll ever get is 99.99 or whatever percent. But it never ever is fully 100% efficient. That never happens. Okay, so work input versus output. Okay, so think about the two possibilities, right? So if you're inputting an amount of work, and you're outputting or you're getting an output, okay? So however much output that you get compared to your input, so output over input, this is a measurement of your efficiency. So if you have less output than you put in, then you're inefficient, right? So let's say you get, like one thing that's quite efficient is an electric heater. They're almost perfect, other than the noise and friction and anything else that could happen inside of them. They're actually pretty good. They're close to the 99.99% efficiency, although there's inefficiencies in getting the electricity to them. The actual electric heaters are pretty efficient. So if you think about it, they're getting whatever the maximum amount of ampage and wattage out of the wall is. So I'm going to say, 200 watts or something like that. No, they've got to be 5 amps. 500 watts. Let's go with 500 watts, okay? They're using up 500 watts coming out of the wall, right? But if they only output 450 watts of actual heat, then you can actually calculate the final percent efficiency. Okay, so that would be, I guess, 90% efficiency. All right, so let's take a look at these couple questions and see if we can answer them here. Find the work input and output for the following situations. Jimmy carries his 7-kilogram backpack to school 750 meters. I'm going to give us a little bit of space. Jimmy here, unfortunately, buddy, you have not done any work because no work. Okay? Because you're carrying your backpack. So the force that you are imposing onto your backpack is in the upwards direction. Okay? Fighting against gravity. Okay, so maybe you carried it about a meter up off the ground, so maybe you did a tiny bit of work, but pretty much nothing, right? Whereas the movement is in the horizontal direction. So there's no work here. There you go. Mr. Drigger pushes a semi-truck with 250 newtons, but it doesn't budge. Well, again, if it doesn't have any movement, right? No movement means no work. Okay, I pushed a lot, right? It's case number 1. I pushed a lot, but no movement. Driving to school takes 5 times 10 to the 6 joules of chemical energy from gasoline. It moves the car 650 newtons, a total of 4.0 kilometers. So what here is the input and what is the output work? Well, this is the input right here, right? This is what it takes. So this is the input. And the output looks like we're going to have to calculate. So right here, this is the output. Let's see if I can just grab my calculator. So 650, I don't know if this is accurate, I just made up these numbers, times 4,000 meters. So 2.6 times 10 to the 1, 2, 3, 4, 5, 6 joules. In terms of efficiency, I think it's somewhat reasonable, but I don't know if that's actually accurate. Anyways, output. Okay, biking to the park takes 150 newtons of force consistently on the whole trip. Okay, so that is the input in this case. And over here we can see that the person wasted this amount on friction of the chain. But that doesn't actually tell us all that much. That's the amount he wasted, not the output. wasted is not what we wanted, so it's definitely not the output. So let's first get the input. So the actual value is 150 times 2,300 meters, which gives us 3.45 times 10 to the 5 joules. Okay, so this is the input value. Okay, but the person wasted 1 times 10 to the 5, so we're just going to subtract the 2. Minus 1 equals 2.45 times 10 to the 5 joules, or because of sig digs, 2.5. And this would be, I guess, 3.5 if we're going to go with sig digs. We may as well go all the way with sig digs. So this was the input, and this is the output. So I hope that this video helped you guys understand work and energy just a little bit better. And good luck with your work and with the test coming up.